Hello everyone. This is the sixth class on the mechanics of solids. In this class, we will study the twisting couple on a cylinder. Before studying the twisting couple on a cylinder, it is essential to understand what is meant by the modulus of rigidity. Let us have some idea about the modulus of rigidity. So consider a rectangular solid cube as shown in the picture whose lower face is fixed. So you have a rectangular solid cube whose lower face is fixed. What is the lower face here? It is A, capital D, capital C and small c. We have a cube whose lower face is fixed and to whose upper face a tangential force F is applied as shown in the figure. So we have a rectangular solid cube whose lower part is fixed and on the upper face a tangential force is applied as shown in the figure. So what happens to that cube? Because of this tangential force that is applied on the upper face, the point A shift to A dash, the point A shift to A dash, B shift to B dash, and small d shift to D dash, and B to B dash. So the shape of the cube is changed as shown in the picture. And we can say that the line joining the faces, the line joining the upper face and the line joining the lower face is turned through an angle phi. That is, upper face and lower face is turned through an angle phi. That is, since A changes to A dash and D is fixed, we can say that there is an angle ADA dash that is called phi, and this phi is called shear strain or angle of shear. That is, the face ABCD is changed to DA dash B dash C. That is, the face ABCD is sheared through an angle phi. Therefore, this phi is called shear strain or angle of shear. ABCD is sheared through an angle phi to a new position A dash B dash C D. This phi is called shear strain or angle of shear. Now what is the tangential stress? We have applied a tangential force on the upper face. So there is a tangential stress. What is the expression for this tangential stress? It is the force per area of the upper face, because we have applied a force on the upper face of the cube. Therefore, the tangential stress is tangential force divided by area of the upper face, that is F by area of ABBD, that is F by A, where A is the area of the upper face, A, B, small b, small d. Now what is shear strain? Shear strain is represented by phi. Since the upper face is displaced very slightly, we can say that this phi is approximately equal to small l by capital L, where small l is the distance through which the upper face is displaced. Shear strain is small l by capital L. Then the modulus of rigidity or the rigidity modulus of the material of the cube is given by, the modulus of rigidity of the material of the cube is given by n is equal to tangential stress divided by tangential stress divided by shear strain. Modulus of rigidity is defined as tangential stress divided by shear strain, or n is equal to F by A, that is a tangential stress, divided by shear strain is phi. Since phi is equal to small l by capital L, we can write the rigidity modulus n is equal to F by A divided by phi, and that is equal to F capital L divided by A small l. This is the expression for the rigidity modulus of the material of the cube, or rigidity modulus of the material n is equal to F by A divided by phi. This is a very important relation. Consider a cylindrical rod fixed at one end and twisted at the other end. Consider a cylindrical rod of length L and radius R, which is fixed at the top and twisted at the bottom end like this. The cylinder is clamped at the upper end and twisted by a couple at the lower end. Then we can see that because of this, each cross section of the rod rotates in their plane through some angle theta. Each cross section of the rod rotates through some angle, and that angle is called angle of twist theta. Angle of twist theta, that is, when the cylindrical rod is fixed at the top end and twisted at the bottom end, then each cross section inside the rod will rotate through some angle. That angle is called the angle of twist theta. Since it is fixed at the top end and twisted at the bottom end, we can say that angle of twist is 0 at the fixed end, because at the fixed end there is no twisting. Therefore, the angle of twist is 0 at the fixed end, that is top end, and maximum at the free end. Maximum at the free end. Now, before twisting, the line AB is parallel to the axis OO dash. That is, before twisting, the line AB is parallel to OO dash. When the rod is twisted, the straight line AB, initially parallel to OO dash, is rotated and takes the position AB dash. After twisting, the line AB takes the position AB dash. That is, it is rotated through an angle phi. So the line AB rotated through an angle phi to take a new position AB dash. So this phi is called the angle of shear. This BAB dash, that is the angle of shear. Now the angle of shear is maximum at the outermost layer. Why? Because at the outermost layer the displacement BB dash is maximum. Therefore angle of shear is maximum at the outermost layer. If you are moving towards the innermost layer, then this angle decreases, and it is clear that the angle of shear is 0 at the innermost layer. Angle of shear is 0 at the innermost layer. Here theta is the angle of twist and phi is the angle of shear, and the rigidity modulus is F by A divided by phi. Phi is the angle of shear. Now let us understand what is the cause of shearing strain, or how the shearing strain happens inside a cylinder when it is twisted at one end. To understand the cause of shearing strain, you consider the case of the cylinder before twisting. Imagine that you have separated the outermost layer of the cylinder and cut it along AB. You just separate the outermost layer of the cylinder, then cut along AB, then flatten the layer. To understand the cause of shearing strain, you imagine that you have separated the outermost layer and you have cut it along AB and just flattened the surface. Now it looks like a rectangle ABCD. So just imagine that the outermost layer is separated from the rod, cut along AB and flattened. Now this outermost layer has the shape of a rectangle. That is before twisting. Now do the same procedure after twisting. When the cylinder is twisted at the bottom end, what happens? The line AB, which is initially parallel to O dash, will take the position AB dash. That is, line AB is twisted through an angle phi. That phi is called angle of shear. Now at this position, you do the same procedure. That is, separate the outermost layer, then cut along AB dash, then flatten the layer. Now the layer has the shape of a parallelogram A, B dash, C dash, D. Thus we can see that B is shifted to B dash, C is shifted to C dash, and the line AB is rotated through an angle phi. This phi is called the angle of shear. This is how shearing strain happens inside a cylinder when it is fixed at one end and twisted by a couple at the opposite end. Here BAB dash is equal to phi is the angle of shear, and the angle of shear is maximum at the outermost layer and it is 0 at the innermost layer, because at the outermost layer the displacement BB dash or CC dash is maximum. Here theta is the angle of twist. Now let us find the expression for the twisting couple on a cylinder. Consider a cylindrical rod of length L and radius R. The upper end is fixed or clamped and the lower end is twisted by an angle theta. The upper end is fixed and the lower end is twisted by an angle theta as shown in the arrow. The lower end is twisted like this. The lower end of the rod is twisted through an angle theta by applying a couple to its lower end in a plane perpendicular to the axis. So it is shifted like this. It is twisted like this. Now what happens inside the cylinder? A reaction is set up and a restoring couple is developed, and this restoring couple is equal and opposite to the twisting couple. So when you twist a cylinder by fixing it one end and twisting at the other end, there is a restoring couple which is developed inside the cylinder which is equal and opposite to the twisting couple. Now imagine that the cylinder is made of large number of hollow coaxial cylindrical shells of gradually increasing radius. This is the cross-sectional view of the cylinder having radius R. Imagine that this cylinder is made up of large number of hollow coaxial cylindrical shells with varying radius, and the shaded part represent one such cylindrical shell having radius x and thickness dx. Consider one such cylinder of radius x and thickness dx. Now when you twist the cylinder, what happens? A reaction is set up inside the cylinder, and at equilibrium, this twisting couple is equal and opposite to the restoring couple. A restoring couple is developed inside the cylinder. If the twisting couple is in this direction, then the direction of the restoring couple will be in the opposite direction. So at equilibrium, the twisting couple is equal and opposite to the restoring couple. Now when you twist the cylinder at the bottom side, each radius of the base will turn through some angle theta. Each radius of the cylinder, each radius of the base of the cylinder will turn through some angle theta. That is called the angle of twist. You consider a cylindrical shell of thickness dx and a radius x. This is the cross-sectional view of a cylindrical shell having radius x and thickness dx. The side view of the cylinder having radius x is shown on figure B. Figure B represents the side view of a cylinder of radius x. Side view of a cylinder of radius x. The cross-sectional view is shown in figure A. This is the cross-sectional view of the cylinder. Here the thickness of the cylindrical shell is dx. Here theta is the angle of twist. Which is 0 at the fixed end and maximum at the free end. When the cylinder is twisted, what happens to the point B on the cylinder of radius x? It is changes to B dash. Now initially the line AB, which is parallel to the axis OO dash. Initially the line AB is parallel to the axis OO dash. Now when the cylinder is twisted, the point B on the cylinder of radius x is shifted to B dash, so that the line AB is rotated through an angle phi and it reaches the new position AB dash. Remember, this is the side view of the cylinder having radius x, which is a cylinder inside the cylinder of radius r. Here theta is the angle of twist. Now when the line AB is rotated to a new position AB dash, then the angle BA B dash is called the angle of shear. Now before twisting, the outermost layer has the shape of a rectangle. That is, if you cut the outermost layer and flattened out, it has the shape of a rectangle ABCD. Now after twisting, if we separate the outermost layer and flattened out, it has the shape of a parallelogram AB dash C dash D. That is, B is shifted to B dash, C is shifted to C dash, with BA B dash is equal to phi is the angle of shear. Now let us find out the expression for the couple per unit twist. From figure A, we can see that the point B on the rim of the cylinder having radius x is shifted to B dash with an angle theta. Since the radius of the cylinder is x, we can see that this B dash is equal to x theta. That is, from figure A, if you consider a cylinder of radius x and thickness dx, if the point B on the rim of the cylinder having radius x is shifted to B dash, then this B dash is equal to x theta. So our first relation is B dash is equal to x theta. Now from figure B, we have the same B dash that we can write it as L phi. because angle BAB dash is equal to phi and AB is L. We can write BB dash is equal to L phi. That is, from figure B we have BB dash is equal to L phi. Here theta is the angle of twist and phi is the angle of shear. Therefore, from 1 and 2, it is clear that we have x theta that is equal to L phi, or phi is equal to x theta divided by L. That is, the angle of shear or shearing strain is equal to x theta by L. This is our equation number 3. From equation 3, we have two conclusions. That is, the angle of shear or the shearing strain is maximum when x is equal to r. Here phi is the angle of shear or shearing strain. We can say that phi is maximum at x is equal to r. Phi is maximum when x is equal to r. That is, when x is equal to r means at the rim of the cylinder of radius r, phi is maximum. Phi is 0 when x is equal to 0. That is, at the axis, the angle of shear is 0. And phi is maximum at the rim when x is equal to r. Phi is maximum when x is equal to r and phi is 0 when x is equal to 0. We have seen that the rigidity modulus N, that is equal to shearing stress by shearing strain, that we have seen. So we can write N is equal to F by A divided by phi, where F by A is the shearing stress and phi is the shearing strain or the angle of shear. We have N is equal to F by A divided by phi. Shearing stress by shearing strain gives the Young's rigidity modulus N. Therefore, the shearing stress F by A is equal to N phi. Shearing stress F by A is equal to N phi. Already we have the expression for phi as x theta by L. We have seen that phi is equal to x theta by L. Therefore, the shearing stress F by A is equal to N x theta divided by L. Since the rigidity modulus is equal to F by A by phi, we can write the shearing stress F by A is equal to N phi, that is equal to N times x theta by L. Now, what is the shearing force F on the shell? We have taken a shell of thickness dx. When the shell is twisted, it will experience a force F. What is the shearing force F on the shell? Shearing force F on the shell is nothing but A into shearing stress. That is A into nx theta by L, where A is the cross-sectional area of the shell. We have the shearing stress F by A is equal to N phi. Therefore, F is equal to A into N phi. That is equal to A into nx theta by L, where A is the cross-sectional area of the shell. What is the cross-sectional area of the shell? Cylindrical shell, that is 2 pi x dx, because the radius is x and the thickness is dx. The cross-sectional area of the shell is 2 pi x dx. Therefore, the shearing force F on the shell, the shearing force F on the shell is given by 2 pi x dx nx theta by L. The shearing force F on the shell is 2 pi x dx area is 2 pi x dx, then nx theta by L. Nx theta by L. So we have the expression, the shearing force F on the shell is 2 pi x dx nx theta by L, that is equal to 2 pi x square n theta by L dx. 2 pi x square n theta by L dx. Now let us find out the moment of the force about the axis of rotation. How to find out the moment of the force about the axis of rotation? That is, here the axis of rotation is O dash, that is equal to L, and the distance from the action of the force to the axis of rotation is x. So basically moment is the force into the perpendicular distance. Here the perpendicular distance is x. Therefore the moment of the force about O dash means force into the distance from O dash. Force into perpendicular distance from O dash, that is the moment of the force about O dash is F times x, that is 2 pi x square n theta by L dx into x, and that is equal to 2 pi x cube n theta by L dx. 2 pi x cube n theta by L dx. This is the moment of the force F about O dash. Now let us find the twisting couple on a cylinder. Imagine the cylinder is made up of large number of coaxial hollow cylindrical shells having the radius varying from 0 to r. So if you integrate the moment of the force about O dash from 0 to r, that will give the twisting couple on the whole cylinder. The twisting couple on the whole cylinder is integral 0 to r 2 pi x cube n theta by L dx. That is, by integrating the moment of the force from 0 to r, we will get the twisting couple on the whole cylinder, and that is equal to 2 pi n theta by L x raised to 4 by 4 from 0 to r. That is 2 pi n theta by L r raised to 4 by 4, and that is equal to pi n r raised to 4 theta divided by 2L. This is the expression for the twisting couple on the whole cylinder. Just integrate the moment of the force about O dash from 0 to r, we will get the twisting couple on the whole cylinder. Now what is the couple per unit twist? Twisting couple on the whole cylinder divided by theta is the couple per unit twist. Find out the twisting couple, then divide by theta, we will get the couple per unit twist. Since the twisting couple is pi n r raised to 4 theta by 2L, the couple per unit twist is pi n r raised to 4 by 2L. The couple per unit twist is C is equal to pi n r raised to 4 by 2L. We represent it by the letter C, couple per unit twist as C. Here C is also called the torsional rigidity. C is also called the torsional rigidity. Let us find out the expression for the couple per unit twist in the case of a hollow cylinder having inner radius R1 and outer radius R2. The twisting couple is given by integral R1 to R2 2 pi nx cube theta by L dx. The twisting couple is integral R1 to R2 2 pi nx cube theta by L dx. And this is equal to 2 pi n theta by L, 2 pi n theta by L then integral of x cube dx is x raised to 4 by 4 from R1 to R2. This is equal to pi n theta by 2l into R2 raised to 4 minus R1 raised to 4. This is the twisting couple. Twisting couple divided by theta will give the couple per unit twist C. Twisting couple divided by theta gives the couple per unit twist C. The couple per unit twist C is equal to pi n divided by 2l into R2 raised to 4 minus R1 raised to 4. We are studying the twisting couple on a cylinder. In this section, we will prove that a hollow shaft is stronger than a solid shaft of the same mass. A hollow shaft is stronger than a solid shaft of the same mass. Stronger shaft is difficult to twist. If the shaft is stronger means it is difficult to twist. What does this mean? The twisting couple is greater for stronger shaft. If we have two shafts, then the twisting couple is greater for the stronger shaft. Consider two cylindrical shafts of the same length, mass and density. One is solid shaft and other is hollow shaft. So we have two cylindrical shafts of same length, mass and density. One is solid shaft and other is hollow shaft. On the left hand side we have a solid cylindrical shaft with the length L and the radius R. This is a solid cylindrical shaft. On the right hand side we have a hollow cylindrical shaft with the inner radius R1 and outer radius R2. The length is the same L. So we have two cylindrical shaft of same length, mass and density. One is solid and other is hollow. Now consider a solid cylindrical shaft. What is the torque necessary to twist this solid cylindrical shaft by theta? That is, what is the twisting couple for this solid cylindrical shaft? Let it be tau, and that is equal to pi n r raised to 4 theta divided by 2l. That is, the torque necessary to twist solid cylindrical shaft tau is pi n r raised to 4 theta by 2l. Now what is the torque necessary to twist a hollow cylindrical shaft by theta? Let this torque be tau dash. It is actually the twisting couple for hollow cylindrical shaft, and that is equal to pi n r2 raised to 4 minus r1 raised to 4 divided by 2l. Now let us find out the mass of the solid cylindrical shaft. What is mass? Mass is density into volume. What is volume? It is pi r square L. Therefore, mass of the solid shaft is pi r square L rho. Now, what is the mass of hollow cylindrical shaft? It is pi r2 square minus r1 square L rho. This is because pi r2 square minus r1 square L is the volume of the hollow cylindrical shaft. Since the two cylindrical shafts has the same mass, we can say that mass of the two cylindrical shaft are equal. Therefore, pi r square L rho is equal to pi r2 square minus r1 square into L rho, because these two cylindrical shafts has the same mass. From this we will get a relation r square is equal to r2 square minus r1 square. Now let us give the proper numbering. We have equation 1, equation 2 and also equation 3. Now equation 2 by equation 1 implies tau dash by tau, that is equal to r2 raised to 4 minus r1 raised to 4 divided by r raised to 4. Now this is equal to r2 square plus r1 square into r2 square minus r1 square divided by r raised to 4. Already we have r2 square minus r1 square is equal to r square. From equation 3, we have r square is equal to r2 square minus r1 square. Now substitute the value of r2 square minus r1 square as r square. Then tau dash by tau become r2 square plus r1 square into r square divided by r raised to 4. Now this is equal to r2 square plus r1 square divided by r square. r2 square plus r1 square divided by r square. From equation number 3, we have seen that r2 square minus r1 square is equal to r square. Since r2 square minus r1 square is equal to r square, we can clearly say that r2 square plus r1 square is always greater than r square. r2 square plus r1 square is always greater than r square. Why? Because r2 square minus r1 square is r square. Therefore, r2 square plus r1 square is always greater than r square. When r2 square plus r1 square is greater than r square, what happens to tau dash by tau? When this condition is satisfied, the RHS of the above equation is greater than 1. Therefore, tau dash by tau, that is greater than 1. Or we can say that tau dash is greater than tau. Or tau dash is greater than tau. Tau dash is greater than tau. We got a relation tau dash is greater than tau. What is tau dash? Tau dash is the torque required to twist hollow cylinder. Tau dash is the torque required to twist hollow cylinder. Then what is tau? Tau is the torque required to twist solid cylinder. That is, we have the result torque required to twist hollow cylinder is greater than torque required to twist solid cylinder. We have already seen that the twisting couple is greater for stronger shaft. What does this mean? It means that more torque is required to twist a stronger shaft. Since tau dash is greater than tau, torque required to twist hollow cylinder is greater than solid cylinder. Hence, we have a hollow shaft is always stronger than a solid shaft of the same mass.